Today, we're going to talk about one way of figuring out whether a sentence is grammatical. In linguistics, a grammar has a fairly formal definition. We're going to talk about how that's defined. We're going to explain what a context-free grammar is, and then in future videos, we'll talk about how you can use a probabilistic interpretation of that grammar to tell whether a sentence is grammatical. And it allows a computer to detect whether a string is grammatical by giving a probability distribution that shows how likely this sentence is to have come from some specified grammar. Okay, but first, what's a grammar? One way that linguists thought about this question was using parse trees, hierarchical structures that encode the grammatical structure of how a sentence fits together. In natural language processing, there are two main ways of creating parse trees. Parsing, in the lingo, constituency parsing, and dependency parsing. Today, we're talking about constituency parsing. It's a little bit more rigorous and older than the alternative of dependency parsing, and it's a good fit for English and many other European languages. When we talk about dependency parsing, we'll talk about how these assumptions break down for other languages. The way that we do constituency parsing is with a mathematical concept called a context-free grammar, which, like many of the other models we'll learn about, can be estimated from data. We'll get there soon, but first I need to tell you what a context-free grammar is. A context-free grammar is defined as a set of four elements. First, a set of non-terminal symbols that correspond to latent syntactic structures, such as noun phrases or verb phrases, and they often correspond to multi-word syntactic abstractions. We don't actually see them in a written sentence, but we believe them to be there. These non-terminals are often called multi-words and are tacit abstractions of how the grammar is structured. The second element are sets of terminal symbols. These are the things that we actually do see. Thus, they are words like dog, the, Pokemon. These are called terminals because when you see them, you stop producing stuff. Non-terminals let you keep going, in contrast. But now you're probably asking yourself how non-terminals and terminals fit together, and that's where the last bit of a CFG comes into play, productions. A non-terminal can produce more non-terminals or terminals. More formally, a production has a left-hand side and a right-hand side. The left-hand side always has a non-terminal, and the right-hand side has any collection of terminals and non-terminals. Thus, you can go from non-terminals to non-terminal, or you can go from non-terminal to terminal, but you can't go from terminal to non-terminal. Otherwise, they wouldn't be a terminal, would they? Finally, we have the start symbol. We anoint one of the special non-terminal symbols as the thing that defines what makes a grammatical sentence, and we'll see why this is important in just a second. This context-free grammar formalization is pretty flexible. It allows you to have unary rules that attach to some sort of syntactic structure and to individual terminals. Hopefully, you can see how this could, say, recapitulate a part of speech analysis. But what about this context-free business? This is a little like the Markov assumption that we talked about before. Once you condition on a non-terminal, the rest of the context of the sentence doesn't matter anymore. Now, if you speak a language other than English or Mandarin, two morphologically impoverished languages, you might think that this is game over. How can something like this capture grammatical features such as case or numbers? For instance, in English, once you're in a prepositional phrase, it doesn't really matter what the preposition was. You can be under any noun. In other words, the context doesn't matter. But this isn't the case, say, in German. Some pronouns require the nouns to match the case of the pronoun. So if I say with, under, or because of the bus, the determiner is always different. And sometimes, so is the noun, as in wegen des Busses. But the grammar doesn't know how to do this. Once you go from prepositional phrase containing a preposition and a noun phrase, all is lost. The preposition doesn't know what is going to be generated. It could be with or under. And the noun doesn't know what case it should take on. But you can subdivide this by having a non-terminal with a feature that explicitly says what its case is. So for the accusative case, the prepositional phrase knows it's going to be an accusative preposition, so it propagates that down to the preposition and then down to the noun and determiner so that it matches up. Then, if you have a dative prepositional phrase, you only generate dative pronouns and dative determiners and nouns. Same thing for the genitive. But if you know German, you'll realize that this isn't all you need. You also need to have the gender in here as well. So you'd need to put that in at some point. If not on the preposition, then at least on the noun phrase, so that the determiner matches the noun. And you can go even further than this by using so-called lexicalized grammars that we'll talk a little bit more about later. But that's beyond the scope of this class. Other fancy things you can do are having empty terminals if you have optional components in a syntactic rule. You could express that, say, using an empty terminal. An example of this is pro-drop in Spanish. The last thing to talk about is the derivation. A derivation is a sequence of steps that take you from your start symbol to a complete sentence of terminals. At each derivational step, you replace one of the non-terminals in your current parse tree with some rule. So pick a non-terminal leaf in your tree that tells you the left-hand side of the rule that you need to use. You look in your grammar for all of the rules that start with that left-hand side, pick any one of them, and then you replace that non-terminal with the things on the right-hand side of the rule. Let's take a look at an example of this. Here we have some grammar defined by a bunch of reductions. Let's start our derivations. So for our first derivation, we have no other choice but to start with the start symbol. So we replace the start symbol with some rule from our grammar. It's now an NP-VP. Again, NP in this derivation becomes det, and then noun. Then we can fill in the determiner with the. The noun becomes a cat, and then we replace the verb phrase with a single verb, and then we put in the terminal. And that's it. We have a sentence with only terminals, and so this means our derivation is complete. We can't go any further. We only have terminals left. And so this is how you go from an empty parse tree to a complete sentence. Sometimes people will talk about this as the yield of the parse tree. What words did it produce? But a context-free grammar is a generative model. It goes from a start symbol to a non-terminal to terminals. You have generated a sentence. But that's not what we actually do in practice. Just like a hidden Markov model is not a good generative model, this isn't a good generative model either. What you actually do in practice is go from a sentence to a tree. More formally, we call the set of admissible parses TG, given some grammar G. So if TG of a sentence is 0, then the sentence is ungrammatical, and if TG is greater than 0, then it's grammatical. But the fun starts when TG is non-zero, but greater than 1. So if you take the sentence, "A man saw the dog with the telescope," under some grammar, there could be two different parses that sentence could produce. What is the phrase "with the telescope" actually modifying? Is it part of the noun phrase that includes the dog? You're talking about a dog with the telescope. Maybe the dog has a telescope strapped to his back or something. Or is it part of the verb phrase, the manner in which the dog is seen with the telescope? But this just tells us that the two interpretations are grammatical. Does this actually help us in any way? What we really want to know is which is more likely. To answer that question, we'll need to extend these context-free grammars to encode probabilities. And that's what we'll do in the next video. This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.